Hi everyone, welcome back to our second lecture. So George is going to tell us more about RSL with Jonah and Jennifer and Mark on a raising operator formula for Macdonald polynomials.
All right.
George.
Yeah. Thank you everyone for being here again. I wanted to throw up some things from last time. And now since we're moving on to a second lecture, if there's ever a confusion about what something is, please don't hesitate to interrupt me and just ask. But just a reminder, so some of the things we talked about last time is we talked about this Weil symmetrization operator where you're given some Laurent polynomial and you can symmetrize it. And in particular, when you symmetrize a monomial, you get out an irreducible GLL character indexed by an arbitrary integer vector. However, there are relations among those those symmetric Laurent polynomials. So you can, given one indexed by any integer vector, you can rewrite it into one where the integer vector is sorted from in decreasing order via this what I call a straightening rule. And you might introduce a plus or a minus sign when you do it, or it might just become zero based on this rule that we talked about last time. And then, of course, if when you sort it, all of the parts that remain are in decreasing order and all greater than or equal to zero, you're actually left with a Schur polynomial. And in fact, like if you sort of unravel everything I just said, this is a definition that is sometimes given of a Schur polynomial, especially if you come from like a more rep theoretic background. And so then we want to define, or we'll use a lot this polynomial part operator that takes a symmetric Laurent polynomial where we've written it in terms of these GLL characters indexed by decreasing integer vectors. And it'll either send it to the corresponding Schur function indexed by a partition if the index you started with was a partition, or otherwise it sends it to zero. And then when we apply this, we're really thinking about it as what's called a symmetric function, where we imagine we have an infinite number of alphabets. Okay. So today I want to get into what last time we didn't talk about was Macdonald polynomials, even though that's sort of what this paper is about. So today I'd like to sort of move to that. But to get there, I first want to start with talking about something called LLT polynomials. Okay. So the why do I want to talk about that? Well, so yeah, I said really the goal is Macdonald polynomials, right? Macdonald polynomials, which is also a little ambiguous because really Macdonald defined gave us really many different, or well, I guess two different you know he gave us different bases of symmetric functions with coefficients that are rational functions in two parameters, q and t. And they the sort of the point that he came up with here, or one of the main points, was that if you specialized these q and t parameters, then you recovered many well-known bases of symmetric functions. So, well, I mean, including, at the time, I think pretty much every sort of one parameter, even the one parameter bases, so including. So in particular, one of those special one parameter bases are the Hall-Littlewood polynomials that we talked about last time. So now one sort of variant that was discovered is called the modified Macdonald polynomials these days. Modified Macdonald polynomials. And these are typically denoted by writing h with a tilde over it, sub mu for a partition, and the symmetric alphabet x with parameters q, t. Okay. And these, so we'll say that they generalize our Hall-Littlewood polynomials are modified ones. From last time. Okay, so they via what I do is you just set the q parameter equal to 0, and you recover what last time I was calling, this is indexed by mu, what I was calling h tilde x t. Okay. And so really, like I said in the last talk, this is very non-standard notation, but this is very standard notation. So from now on, when I'm referring to these, what I called modified Hall-Littlewood polynomials, I'll just write it in terms of this Macdonald polynomial form, but I didn't want to do that last time because then there would have been this extra 0 floating around. Okay. Now, there's a few different ways to get at Macdonald polynomials, and what they are. But for our purposes in this paper, we have the benefit of 20 plus years of research behind us. And so we can really make use of a result by Hagelin, Heyman, Lohr, who give a combinatorial formula for these Macdonald polynomials. So, so Hagelin, Heyman, Lohr. Give combinatorial formula for our Macdonald polynomials. But they do it via something that is called an LLT, or via a family of polynomials called LLT polynomials. So, which are also nicely combinatorially defined. So I want to first start by telling you about the LLT polynomials, because then we can describe this Hagelin-Heyman-Lohr formula to get a nice definition of a Macdonald polynomial. Okay. So let's start with some combinatorics. So just like in my last talk, I'm going to do all of my diagrams are going to be in French notation. So I'm imagining everything sort of in the first quadrant of an XY plane. And so in particular, when I talk about boxes, I'm going to index them by like their X coordinate comma their Y coordinate. So the box, let's say B with X coordinate I, Y coordinate J of a skew diagram. So if you're not familiar with a skew diagram, right, all we are doing, so let me say new, is we take a partition, say lambda, and then we delete some smaller partition from the bottom left, and that smaller partition is mu. And then for every one of these boxes, we're going to define the content of the box to be I minus j. So let's do an example, just because that will make it, I think, clear. So here, I had pre-drawn a skew diagram. So this would be the partition 3, 3, and then I've removed the partition 1 from the bottom left corner there. And if I'm thinking about this in the XY plane, then along the line that is the y equals x, I'm going to have 0 content, right? So this box has content 0. And then here we have right in the box to the left, it's 1 minus 2, so -1, and then 1, 1, and 2, and so on. So these are the content diagonal or content fillings. So then when I want to really be let's see, yeah. So then let's say I have a whole tuple. So given a tuple of skew diagrams, sorry, let me move that down one. Or given a tuple, let's underline it, bold new of skew diagrams, new sub one, just say new sub k. We are going to give this is of skew diagrams, right? Then we want to put a reading order on the boxes in all of these things. So let's take a reading order on all the boxes and new given by aligning the content diagonals of all the shapes and diagonals. And let's read sort of one diagonal at a time in increasing content order, diagonal by diagonal, in increasing content. And let's read each diagonal starting at the southwest and moving to the northeast. So maybe once again, this is best illustrated by an example. So let me grab an example here, move it up. Okay, so our example here, we have two skew shapes. So the first one is say 3, 2 with the box 1 removed. And the second one is 3, 3 with the shape 1, 1 removed. So the reason I'm sort of doing it this way is we have these content diagonal labeling. So let's see, here's 0, -1, 1, and 2, right? So I've taken these two shapes and I've aligned them in my plane so that their contents line up. And then what I'm saying is we'll just read starting with the smallest content diagonal. Here's -1, and we'll move sort of just in this direction for our reading order. So our boxes, right? This would be the first box, and then we have the second box, third, fourth, fifth, sixth, seventh, and eighth. Okay. So is this I hope this is reasonably clear. Like, yeah, it's just sort of a very like we just take the things, we put them in the plane, and then we sort of sweep moving along the diagonals like that. Okay. Now and so ultimately the reason we're talking about these tuples of skew shapes is because this will be the indexing data for our LLTs. But LLT polynomials also have an extra Q parameter. And so we need to talk about something called attacking combinatorics in order to describe that Q parameter. So let's talk about another definition. So if we have some boxes in our skew shapes, let's say A in nu sub I, B in nu sub J, with I not equal to J. So they're in two different shapes in this tuple. Then we say that they are an attacking pair if, first of all, let's just fix A less than B in reading order. So this is reading order. And then either one of two things happens. So either one, the shape I precedes the shape J in the tuple. And then in that case, we have that the content of A is equal to the content of B. Or if the shape of A that A is in comes after the shape that B is in, then the content of A is equal to the content of B minus 1. Okay. So let's just do some examples of that. So here I have the same example from above with the reading orders filled in. Okay, and let's just look at each case separately. So let's do the first type. So going for the first type, we just go in reading order and we look to see if there are any boxes happening that are come after let's say box A with the same content. So if we start at 1, well, there are no boxes beyond this way that have content minus 1. But if we look at 2, well, 2 attacks 3 because 3 comes here in a later shape, and they have the same content. So let's just draw this arrow to indicate that they're attacking. But then 3 has none of the type 1 attacks. And then let's look at 4. Well, 4 attacks 5, and 4 also attacks 6 because, right, they have the same content diagonals, but 5 and 6 come in a later shape. And similarly, 7 attacks 8. Okay, so that's the first type, but then there's this other type, second type, and maybe that's a little less straightforward. So for this one, I like to think about it as you start at a spot and then you kind of wrap around and look at everything that you hit before you come back to where you started. So like, let's look at, say, box 3. So box 3 is in content diagonal 0, and then if I sort of continue my reading order, I move on to content diagonal 1, and here I hit this box 4 before I've returned to this shape that 3 is in, and so 3 attacks 4. Okay. Similarly, 5 will attack 7, and 6 will attack 7. Okay. And so then in total, this tuple has 7. So this has 7 attacking pairs of boxes. Okay. And so these attacking pairs are going to be what we build our Q parameter off of. Okay. So now I can give you the combinatorial objects that we'll use to actually define these LT polynomials. So I guess I've never defined a semi-standard Young tableau in this talk, but right. So let's see if I want to define the idea of a semi-standard Young tableau on a whole tuple of shapes. So this is a map, let's say, that goes from the boxes to let's say positive integers, such that when I restrict this function to one of the shapes in my tuple, like nu I, then this is a semi-standard Young tableau on that skew shape. And right, so a semi-standard Young tableau is just, for those who aren't in the know, right, this is a filling that is increasing along rows and strictly increasing as you move up columns. Okay, because we're in French notation. Okay. And then, right, so that's just sort of giving us a bunch of fillings of numbers and boxes. So then where does this attacking combinatorics come in? So then we have, for a tableau, we'll define an attacking inversion in this tableau. So this is an attacking pair AB such that T of A is greater than T of B, hence the name inversion. So this is right because you have the preceding thing in earlier in reading order being greater than the later thing. And so we'll set inv of T to be the number of attacking inversions. Okay, so let's do an example where on this tuple of skew shapes that we already have. So let's fill this with some numbers, say 2, 4, 3, 5, 1, 1, like this, right? So here I have a filling where in each shape, it's a semi-standard Young tableau. And then I just need to look, right, go over to get this extra data about the inversions. I just need to look at all these attacking pairs I already computed and check for an attacking inversion. So, right, for the box with a 4 attacks the box with a 5, but that's fine. They're in order. But then this box with a 5 attacks this box with a 3, but 5 is bigger than 3. So we have an attacking inversion right there. Similarly, this box with a 3 attacks this box with a 1, but right, that's a decrease, so it's an inversion. But 3 is not bigger than 6, so that's fine. 6 is bigger than 5, so that's an inversion. And finally, right, 5 is bigger than 1, so this is an inversion. Okay, so these are the attacking inversions of this tableau. And so the inversion statistic spits out a 4 because there are 4 of them. Okay. And so now we have the combinatorial ingredient. We need to define these so-called LLT polynomials. So let's do it. So given nu, right, to be a tuple of skew shapes, then our LLT polynomial is so it's typically denoted with some kind of script G, and we index it by this tuple of skew shapes, and it'll have this extra parameter Q, and so it's a sum over all the semi-standard Young tableau of nu with so x to the t, where by that I just mean, right, I take the product of all of the boxes in nu and evaluate the tableau on this box. So I'm just taking all the numbers and those contribute x monomial factors. And then I'm putting in front of it a q to the inv of t. Okay. So let's do also an example, which I've started. I wrote out some tableau for a given shape right here. So UG. So now I've picked a slightly different tuple just to make the tableau a little simpler. So I have 2 skewed with 0, 3 skewed with 1. Okay, so it's just two rows of length 2, but they're aligned so that right, the only attacking pair is the second box in this row is attacking the first box in this row. Okay, and then right, if I wanted to evaluate using this formula, my G nu, right, I would have to really write out like every single tableau, right? So like this one is x1 contributes an x1 to the 4th. There's no attacking inversion. This one though, right, we have an attacking inversion right here. 2 is attacking the 1. And so we get q x1 cubed x2. And then this one, there's no attack, so we just have x1 cubed x2 and so on. And of course, I would have to write out maybe a decent number of tableau before I really see the whole pattern here. But also if you know that Schur polynomials are given by a similar formula without a Q, you can kind of just do a case-by-case analysis on these tableaux and work out a Schur expansion in this case. So you get S4 plus Q S31 plus Q S22. I don't expect anyone to do that quickly, but just, for sort of for your information, it does actually work out to be this Schur polynomial expansion. Okay. So some facts about this, like how do we think about these things? Well, I mean, it's not obvious from the definition that I gave up here that you even get a polynomial that would be symmetric, but it is. So nu is symmetric. Okay, non-trivial, but not too difficult to show. Oh, I should have mentioned that this LLT stands for Lescaut, Leclerc, and Thibon, and they're the ones who sort of invented these or discovered these LLT polynomials and showed that they're symmetric, although they didn't necessarily do it in this form. And so you can also find a symmetry proof in this Hagelin-Heyman-Lohr paper that that I talked about before. But the other way that I like to think about LLT polynomials is that, and this, if you're sort of new to any sort of like Q or parameter type deformation thing, it's nice to set parameters, say to 1 and see what you get. And in this case, you would just get a product of the Schur functions involved in your tuple. So in some sense, right, an LLT polynomial is a Q deformation of a product of Schur functions. So I think that's all I want to say about LLT polynomials right now. Are there any questions about this before I move on to talking about Macdonald polynomials?
Yes. Hi.
Yeah.
Question.
Yeah.
So these don't usually, I mean, the order in which you take your tuple, it is a tuple matters, right?
Yes. Yeah. The order matters.
So is it known when it doesn't matter? Like when you switch things in the tuples and it would commute?
Right. So there is like a rotation rule where you can take like the top shape and move it down, but then at the when you do that, you have to shift everything one content diagonal to the right. And you can sort of work out from the definition of attacking inversions and attacking pairs that this would preserve all of your attacking pairs and the reading order of all the boxes. And so I guess like if you do, you can sort of iterate that rule many times. And if you sort of have something that's reasonably stable under that, like that's sort of known. But I think beyond that, I don't know, there's some other special cases where maybe it would be known, but
dominoes, just
mm-hmm.
row with 2 cells and a column with 2 cells.
Yeah. Mm-hmm. Yeah, I think the order matters at least a little bit. I mean, like in this example that I did here, where we have dominoes, right? Like, if I had changed the order, now my attacking combinatorics would be different. Because then if I reverse the order on this, I would have like and I put the one with 0, 1, 1, 2. Right now this let's see, this box attack. Well, yeah, now we have sort of a chain of attacking pairs like that, right? So it changes the Q combinatorics significantly.
Okay.
Yeah. But yeah, maybe we can talk more about that later about when you
Sorry.
might expect. No, it's a good question. And I think I want to be building the intuition about these things a little bit while we talk about them. So yeah, it's a good question.
I
Thank you.
think that for the domino case, it is proof that you can just change the order.
In what sense? Well, you're saying that in this case, this one will actually give me the same LLT polynomial?
Yeah, and for like
Oh,
you
okay.
you can actually do like vertical and horizontals.
Okay, cool. Yeah,
Yeah.
I didn't realize that. Okay. Yeah, I guess I wouldn't. That's somewhat surprising to me, but I guess it's doable. But it's not obvious from the definition that I gave anyway. Okay, cool. All right. So then let's talk about Macdonald polynomials, sort of the subject of all of this. So Macdonald polynomials via, I want to sort of do it in the style of Hagelin, Heyman, and Laura's work, as opposed to some other sort of more geometric or algebraic approaches. I really want to get into the combinatorics here. So let's start with if I have some integer vector of, let's say, positive entries only, then I want to define a column diagram of this, which I'm going to call B star. And this is going to be given by taking boxes in the first quadrant, and I'll go over my x coordinates will just vary over my entries in the this integer vector beta, and I'll have a column of height beta I for each entry. So right here's an example. So if I take beta, be 2, 4, 3, 4, 3, then here's my column diagram. Right, and it's just heights 2, 4, 3, 4, 3, left to right. Okay. And right, just to really orient ourselves, right, like for our Calc 1 students type thing, we're still sort of thinking about everything in the XY plane. So like that is box 3, comma 2. Okay, and sort of remark why am I using this star type notation? Well, so if beta were a partition, then beta star is the diagram of mu. So it's sort of like, right, yeah, I guess like the point is like if I had a partition, this diagram that I draw out is really like the conjugate diagram or the transpose diagram of that partition. So the star is just to kind of help us keep track of that mentally, if you're used to working with partitions. Okay. And so then the combinatorics for this Hagelin-Heyman-Lohr formula are going to come out of these sorts of diagrams. So I need to associate some statistics on these diagrams. So if I have some box in my column diagram, and let's just do it on boxes that are above the first row, so j greater than 1, then let's set, it'll be called the leg of the box, going to be beta I minus j, which is just the number of boxes strictly north of our box B, and the arm. So this one's a little bit more complicated, and maybe instead of writing out a formal definition, I'll just kind of say it's the number of boxes that are strictly east of the box, or of B in columns, let's say I prime of height beta I prime less than or equal to beta I. And then we'll also add the number of boxes that are strictly west of, well, I'm going to write south of B, maybe without defining it. I just literally mean if I have a box here, the south of B is the box that's one below to the south. Okay, so it's strictly to the south in columns I prime of height, where beta I prime is now strictly less than beta I. Okay. So let's just do an example. Right, so if I pick my box B to be this box 3, 2 right here, right, well, the leg is going to just be the boxes strictly to the north. So the only box in its leg is right there that I filled with an L there. And then the boxes in the arm, well, so I go east and I look only at columns whose heights are less than or equal to the height of this column that B is in. So this column is excluded from my consideration because it's taller. But then this column is the same height. So it has this box right here contributes to the arm. And then going west, so I look at south of B, which is down here, and I look into columns whose height is strictly less than 3 in this case. So right, this column of 4 is excluded, but the column of length or of height 2 is not. So this box also contributes to the arm. So you're just scanning, right, like this way and this way, and checking for columns whose heights are and on this side exactly equal or less than or equal, and on this side strictly less than. Okay. And so why I'm sort of a foreshadowing is, right, I'm introducing leg and arm because I'm going to end up needing some Q and T type statistics, and so I need 2, and these will end up contributing Q and T factors. Okay, so the other thing I'll need is I'll want to take these boxes and sort of come up with ways to construct LLTs from them. And so to do that, I want to also give this column diagram a reading order. I'm going to give it, though, sort of the one that we've been using all day on reading text, which is we're going to read the boxes left to right and top to bottom. As if we were just reading them as English text. Okay. And then we will call the kth box. I'm going to need to be able to refer to it. So I'm going to call it beta, and then I'm going to put square brackets k, so that we're not confusing it with like the kth entry of beta. This is the kth box in reading order. And then some more notation. Let v, the beta, be the pairs of vertical dominoes in this box. So I'll write it out sort of formally, right? It's the pairs of the ith box and the jth box, such that the jth box is directly south of the ith box. Okay. So right, this is just the set of vertical dominoes in beta star. Okay. So now let's see. So then if I take some, what I'm going to do is I want to ultimately be able to take take each column in this diagram and sort of chop it apart into pieces, but then I might want to turn these columns into ribbon shapes, and I'm going to do that by picking some kind of set of vertical dominoes. So for any subset of our vertical dominoes, we construct a tuple of ribbons, we'll call them. Okay. And I'll denote them that nu of S, because it's being controlled by this choice of dominoes from our columns in beta star. And, instead of writing this out precisely, I'll just say, and maybe give you an example. So the rows in beta star are going to correspond to content diagonals in nu of S. If we have a domino in S, that's going to force the boxes to become a vertical pair. And if it's a not, so let's say domino not in S, then this will be a horizontal pair in our ribbons. Okay, so let's actually just do an example, because I think that will make it a lot more clear. Okay, so here I've taken beta to be 2, 3. Okay, and then so this is our diagram, beta star. And let's pick maybe, right, so I've written the reading order, so 1, 2, 3, 4, 5, left to right, top down. And let's pick some dominoes. Maybe, let me copy this. So maybe let's pick like 2, 4, and 3, 5. So F is 2, 4, and 3, 5. I should put like a beta square brackets on all this, but right, I'm just saying box number 2, box number 4, and box 3, and box 5. So then what I'm going to do is I imagine that I break up these 2 columns into 2 separate pieces, and by keep them the rows aligned by content diagonal, and any of these vertical dominoes that I've picked will stay vertical. But if a shape is not part of or a pair is not part of a domino that I've picked, then it'll turn horizontal. So let me, as I didn't pre-populate the picture, may intentionally. So here I have 3 and 5, or sorry, 2 and 4, my bad. 2 and 4, and right, so like 2 is going to be on the same content diagonal. Let me give myself more space, as 3. And 4 is on the same content diagonal as 5. And because I picked 3, 5, and 2, 4, those stay vertical. But then because 1, 3, the domino 1, 3 is not in our set, 1 and 3 will be horizontal. And so I draw it like that. Okay. And this construction, sort of by virtue of taking my column and just sort of bending it based on these vertical domino rules, will be what we call a ribbon. And sort of formally, a ribbon is just a shape with no 2 by 2 boxes in it. Okay. So now we actually have everything we need to say what a Macdonald polynomial is combinatorially. So this is called the Hagelin-Heyman-Lohr formula. So if I have some partition say mu, and let's take beta to be any rearrangement of the conjugate of mu, then my Macdonald polynomial is given by, I take a sum over all choices of vertical dominoes in beta. And then I take a product over the dominoes that I did pick. So let's say beta I, beta j in S. Okay. And for each of those, I'm going to get a q to the minus arm of beta I factor times t to the leg of beta j plus 1. And then for each of, so that's just like a product over all the choices of vertical dominoes in the set. And then that will be a weight on the LLT polynomial indexed by the tuple of ribbons coming from that choice of dominoes. Okay, like this. Yeah, and if you want sort of the easiest choice of this, right, you can just take beta to be equal to mu star. So let's actually like do an example. So let's do, say, h21 of x ut. Okay, so of course, if I draw out the column diagram in this case, I only have, so boxes 1, 2, and 3. And there's only one vertical domino here. So I can either have that domino or not. So, right, I'll have the LLT where I have this arrangement where the vertical domino is forced to be horizontal, and I'll have the other one where it's forced to be vertical. Okay. And right, this corresponds to having no dominoes picked in my set, and this corresponds to picking precisely, to having my domino. Okay, and so then reading off the formula, well, this LLT will have no QT factors because I take this product over the dominoes that I picked. So this is fine, that's a 1. And for this one, right, I have to do the one domino. And so it's going to have, well, in this case, the box beta I is going to have no arm because there's no boxes to its right this way and no boxes to its left of its south. And it also has no leg because it's at the top, but there's this +1 factor here, this +1 term, so this whole thing will get a T on it. Okay, and these are LLTs in Q.
So
Yeah.
in the formula, t to the leg of beta I.
Oh, yes, you're right. Yeah, I, not J. Sorry. I guess, yeah, if I had put J, then I could have removed the +1. Okay. Great. And so then, right, and then just sort of to work it out in terms of Schur functions, just to see what this looks like. Once again, like I don't expect anyone to be able to just like look at an LLT polynomial and Schur expand it quickly in their head. But this first LLT ends up contributing an S3 plus a Q S21, and the other one contributes, multiplying it by T, it's a T S21 plus QT S 111. Okay. So we see in this already example, like Q's and T's showing up in non-trivial ways in this expansion. Okay, so I don't have a ton of time left, but maybe let's just like end on talking a little bit about the Macdonald polynomials and some of the things that make them interesting and worth studying. And then next time we can actually get into this new formula for them. And of course, one fact that isn't clear from the definition, but I sort of have already said, is that these things are actually a basis for symmetric functions with parameters in rational functions in Q and T. This is maybe more immediate from other definitions, but in the Hagelin, Heyman, Lohr paper, they show that this combinatorial definition satisfies sort of nice triangularity properties that are necessary or that you can use to give a basis. But also sort of a thing that attracted a lot of interest, right, in these Macdonald polynomials to begin with was that when people programmed them on a computer and they expanded them into Schur polynomials, like I've done here, they noticed that the coefficients were always polynomials in Q and T with non-negative integer coefficients, or what people started calling, for short, they would say Schur positive. Okay, and there are many reasons to care about Schur positivity, but maybe one of the biggest ones, two big ones, is one, if you have things that are all sort of non-negative integer coefficients, as combinatorialists, we like them because that means they're counting something, hopefully. And specifically with the Schur basis, this means that one would hope for a representation theoretic interpretation of these Macdonald polynomials. And that program was sort of carried out in the late 90s and early 2000s and sort of culminated in Mark Heyman actually showing that these Macdonald polynomials are Schur positive by showing that they actually are the bi-graded characters of some symmetric group module. If you don't know what that means, don't worry about it because I'll never say it again in this talk. But the sort of combinatorial upshot is that these coefficients, right, lie in this polynomial ring that they lie in this set where your polynomials have non-negative integer coefficients, and we call this Schur positivity for short, or we say it's Schur positive. But sort of in the course of all this study, so it took a little while, maybe like 10 years between observing this fact on the computer and actually Mark giving his proof using sort of geometric means. And one of the sort of really interesting things that popped up in the interim was people noticed that there was this operator called nabla on symmetric functions for which the Macdonald polynomials were an eigenbasis that ended up sort of simplifying some combinatorics and leading to some other really beautiful results. So maybe let me just conclude by defining that. So we have nabla is some operator on symmetric functions be given by the linear extension of when we apply nabla to a Macdonald polynomial, we just get a monomial in Q and T times that same Macdonald polynomial. So Q to the n of mu, T to the n of mu, H mu x ut. Okay, where n of mu is just the sum over I of I minus 1 times mu I. So a relatively easy number to compute. Okay. And sort of this launched a whole industry of various really beautiful conjectures and ultimately results where people then took this operator and applied it to other symmetric functions besides just the Macdonald polynomials. And sort of just a conclusion, and sort of because this motivates how we even started looking at raising operator, or these like, raising operator formula type results, is that well, so early on, Mark Heyman also showed that if you applied nabla to an elementary symmetric function, that this is sure positive. And there's a lot of really beautiful combinatorics where you expand this in terms of LLT polynomials, but that we won't get into that in this series of talks. And then also my collaborators and I, in a different paper than the one we're talking about, were able to provide a proof that when you apply nabla to a sure function up to some global sign, this is sure positive. Okay. And so this sort of suggests that this nabla operator, well, it seems kind of coming out of nowhere from this way I've treated it, it really is doing some really interesting and beautiful stuff, because when you apply it to these other sort of bases that are these other symmetric functions that are not just like floating out here in the definition, you actually get something interesting with some nice combinatorics. So maybe I'll end there today, and we'll then talk about how my collaborators and I approach these things on Tuesday.
Thank you so much, George.
Yeah, no problem.
Any questions for George?
So
Oh,
I
so
have
chats.
So yeah, thank you for the nice talk. And Heyman's result relates nabla en with the diagonal invariant. If I'm understanding correctly, your the BIM's results about nabla sure is giving a LLT expansion, thereby proving the sure positivity. Is there a direct representation theoretic proof, or
No. Yeah, I'm not aware of any sort of modules or even a conjecture in general for a nabla of on a sure. There are some special cases, but yeah, Brendan.
So sorry, so George, isn't there some family of Tor groups that Carlson and Mellett conjecture get a representation theoretic interpretation?
Oh, is there?
Okay.
Sure.
Yeah, but it's not easy to define. Tor is.
Yeah. I think you're right. I haven't studied that paper by them very closely yet. I think I remember hearing about it at OPAC a few years ago, but they hadn't put anything up on archive, and then I just haven't had time to investigate that. But you said it's just a conjecture, or are they able to prove?
Yeah.
Okay. I'll have to look at that then.
Any other questions or comments? All right, if not, then let's thanks George again.
Thank you.
All right, then we'll resume next week. Have a nice weekend, everybody.
All right. Yeah, thank you.
Bye.
Thank you.